students. Today we will start the next chapter. That's chapter number 9. Chapter is areas of parallelogram and triangles. And in this chapter we will study about the relationship between the areas of a parallelogram and a triangle if they lies in between two parallel lines and the same base. So first we have to study the diagrams or figures between the same parallels and on the same base. So our first topic is figures on the same base and between the same parallels. Here figures will mean the geometric figure, for example triangle, parallelogram or rectangle, like this. So here we will study some figures, that is geometric figures between the same parallels and on the same base. So if we draw a parallelogram here, if we draw this parallelogram, suppose A, B, C and D. So its base is CD and it lies between this AB and CD. AB and CD are two parallel lines. Now if we draw another triangle, suppose here, suppose D, sorry, it's E. Suppose ECD is a triangle and ABCD is a parallelogram. Now, in both the figures ABCD and ECD, base is same. That is, base is common. CD is the base, and both are, that is, the other vertices. That is, the vertices A and B of this parallelogram and E of this triangle lie on this line. That is, the other lines, both the figures, the triangle and the parallelogram lies between the same parallels and have the common base here. Similarly, if we draw a rectangle here, it's a rectangle, and if we draw a parallelogram, suppose A, B, C, D. ABCD is a rectangle and CD, suppose E, F is a parallelogram. So both the figures, in the rectangle and the parallelogram, this is the common base. That is, both the figures lie on the same base and between the same parallels, because AB or AEBF is a line and DC, both are parallel lines. Now if we draw, suppose it's a parallelogram A, B, C, D, and if we draw another parallelogram here, suppose E and F. So A, B, C, D is a parallelogram and E, F, C, D, suppose, is another parallelogram. So they have the common base CD, but the other two vertices EF and AB are not the same line. That is, both the parallelograms are not lie between the same parallels. Similarly, if we draw a rectangle here, suppose ABCD or PQRS, any parallelogram, and suppose ECD is a triangle. So, but both the parallelogram and triangle have the common base CD. CD is the common base of both the triangles and parallelogram. but the vertices E and the AB not lie on a same line. That is, both the figures not lies between the same parallels. That is, there are some figures which lies between the same parallels and on the same base, but there are some figures they may lie on the same base but not lie between the same parallels. And suppose here we draw another parallelogram. Here A, B, C, D, P, Q, R. We draw a parallelogram A, B, C, D and P, Q, R is a triangle, and both the figure, that is both the parallelogram and the triangle, lies between the same parallels, because this base and the vertices the same parallels, but the base are not same, because DC is the base of this parallelogram ABCD and QR is the base of this triangle PQR. So DC and QR are not equal. That is, they lies between the same parallels but their bases are not same. So in our exercise 9.1 we have some figures. We have to identify which figures lie on the same base and between the same parallels and which are not. So this is the exercise 9.1. So this is exercise 9.1, question number 1. We have 6 figures here and we have to say in which figures the figures lie between the same parallels and on the same base. And in that case, if the figures lie between the same parallels and on the same base, we have to write the base and the parallels. So first see figure number 1. So here A, B, C, D and so is a trapezium and P, C, D is a triangle. So see clearly both this triangle and the trapezium lie on the same base CD and between this same parallels AB and CD. So it's yes, first one, that is first figure is lie on the same base and between the same parallels. So we have to write the common base, that is same base. What is here? CD is their common base and parallel lines are which one? CD and AB. CD and AB. That is these two figures lies between these two parallel lines CD and AB. Here PQRS is a parallelogram and MNRS is a trapezium. So both these figures lie on the same base SR but not lie between the same parallels, because this figure, this is the MN, this is figure PQ. So PQ and MN are two different lines. So both these figures are not lie between. So its answer is no. That is, it's not lie between the same parallels. So in this figure, if we consider PQ as base, QR as base, then both the figures, that is PQRS is parallelogram. So if we consider QR as a base and PQR as a triangle, so both this, for both QR is the common base and both these figures lie between this same parallels PS and QR. So common base is QR and parallel lines are QR and PS here. PS and QR. So in this figure, So both this A, B, C, D and P, Q are lie between the same parallels but not on the same base. Here base is BC and PQ are two different bases. So here answer is no. Here A, B, C, D is a parallelogram and A, P, Q, D is also a parallelogram, and here AD is suppose considered a common base AD. So then both the figures lie between the same parallels. So yes, so base will be here, that is common base will be AD and parallel lines are, that is lies between the lines AD and BQ. It's BQ. So here BQ and AD parallel. So both the figures lies between these two parallel lines. And here A, B, C, D and P, Q, R, S. Both the figures lie between the same parallels, but not on the same base. So they may lie in the same parallel lines, but they not lie on the common base, that is base are different here. So this is exercise 9.1. So our next topic is parallelograms on the same base and between the same parallels. If there are two parallelograms or three parallelograms or more, but they all lie on the same base and between the same parallels, then what happened? So we have some activity 1 and activity 2 in your book is given, so you can do this activity yourself. Now here we will study theorem number 9.1. So here is a theorem 9.1. So here is a theorem 9.1. Parallelograms on the same base and between the same parallels are equal in area. That is, if we have two parallelograms on the same base and between the same area, that is between the same parallels, that is height are same, then its area will be equal. Let us suppose we have a parallelogram A, B, C, D, and taking CD as common base, if we draw another parallelogram here, and EFCD is another parallelogram, then see A, B, C, D and EFCD are two parallelograms, and both these parallelograms lie on the same base CD and between these two same parallels. Now we have to prove that these two parallelograms have equal areas. So see the proof now. So first we have to write the special statement. Special statement. So here we have to write, let ABCD and EFCD, ABCD and EFCD be two parallelograms on the same base CD, this common base is CD here, and between the same parallels CD and AF. That is AF and CD are two parallel lines, and both the figures, that is both the parallelograms, lie between these two parallel lines. So to prove, what I have to prove? Area of ABCD, that is AR means area of ABCD is equal to area of EFC. Now we have to prove it. Now see the proof part here. So in the proof part, we will take this triangle, these two triangles first. These two triangles first, and in these two triangles, this angle is A and this angle B are equal because AD is parallel to BC and AB or AF is transversal. So both these angles are corresponding angles, and corresponding angles are equal. And similarly, this angle E and angle F are also equal. They are also corresponding angle. And in both this triangle, suppose AD and BC are also equal because opposite sides of ABCD are equal. So by angle side or angle side, these two are congruent triangle, and if they are congruent, then their areas are also equal. So see, in triangle here AED and triangle BFC, we have angle EAD, that is EAD is equal to FBC, angle FBC, right? Corresponding angle, because or since AD parallel BC and AF is transversal. So this is the reason. Next we can write AED, angle AED is equal to BFC, angle BFC is also corresponding angle. Since this ED is parallel to FC, because EFC is a parallelogram, so opposite sides are parallel, that is ED and FC are parallel, and AF is transversal. And we write AD is equal to BC, or you may write ED equal to FC also. It's also equal. We write AD and BC, or you may write FED and FC. Opposite sides of a parallelogram are equal. So therefore, triangle AED is congruent with triangle BFC by angle side congruence. Okay, that is this triangle and this triangle, two triangles. This triangle and these two triangles are congruent. So if they are congruent, then that means exactly same. Their shape, size, side, angle, all are same. That means they must have equal area. Therefore, if they are congruent, therefore area of triangle AED is equal to area of triangle BFC. That is, if it is congruent, then their areas are equal. Now we will add this part, this unshaded part, EBCD, to both sides. So adding area of EBCD to both sides, we have, so area of here triangle AED plus area of this part EBCD is equal to area of triangle BFC plus area EBCD. That is, we add this area of EBCD to both sides. This implies, so last line, so first AED, with this, if we add this part, that is white part, that is, if we add this part, then we get A, B, C, D. That is, we get area ABCD is equal to ABCD. If we get BFC plus this part, we get EFCD. That is area EFCD. So, which is the required proof. That is, this area of ABCD and area of EFCD both are equal and they lie between the same parallels and on the same base. So this proof is very, very important. Okay. So after this theorem number 9.1, we have two examples, example 1 and example 2. But example 2 is much more important than example 1. Here, if a triangle and a parallelogram are on the same base and between the same parallels, then prove that the area of the triangle is equal to half the area of the triangle. And we will use this example as theorem. That is, we will use this property in our sum. That means, if we have a parallelogram here, parallelogram, and we have a triangle, suppose. If we have a triangle, suppose A, B, C, D is a parallelogram and P, C, D is a triangle. Now you have to show that this area of this triangle, area of PCD, this triangle. So both the figures lie between the same parallels and their base are same. Then is equal to half of area of this ABC. That is half the area of this parallelogram. So to prove this sum, we have to make a construction. So we have to extend this AB and this PD. We have to draw a line. Suppose CQ parallel to PD. Now ABCD is a parallelogram given. Again, since it is a parallelogram, that is AB is parallel to CD, so PQ is also parallel to CD. By the question, by construction, this PD and QC are parallel. That is PQCD is a parallelogram now. because both the opposite sides are parallel. So since they are parallel, that means their areas must be equal by this above theorem. That is, we get area of ABCD is equal to area of PQCD. Since both these parallelograms lies between the same parallels and on the same base. So if we multiply by half, then we get, that is, in case of PQCD, PC is a diagonal, and we know that a diagonal divides a parallelogram into two equal triangles. That is, in case of PQCD, if PQ is a diagonal, that means half of this PQCD will be PCD. That is, we get area of PCD. That is, half of ABCD will be area of given triangle. The proof is given on your book, so try it. So this is an important theorem, remember it. Not theorem, but we will use as theorem. Okay, thank you for today.